and oh, sorry. I came along here last year for the first time and learned a lot. Took away a bunch of ideas and bulbs and everything else. I've actually been building my own microcontrollers now for 4, maybe 5 years. It all started with a set of lights like this, which are the GE Color Effects. These were commercially available in the US about 4 or 5 years ago. Basically, they're a microcontroller light, slightly different to the WS2811s and 2801s in that they've actually got addresses, so when you initialize them, you can actually talk to individual bulbs directly. So it's a very different protocol. And at that time, they're not really designed to be hacked, but of course it doesn't take long for someone to reverse engineer the protocol, and once you know the protocol, it doesn't take long to start writing controllers and start to control them. And so we hacked around with these for a while and covered the house in the front of them, put big patterns and everything on. And then last year I came along and found all of these lights, etc. And so last Christmas I built my first controller that runs the WS2811s, which was a bit of a challenge because these are great, and because you can address them directly, it's really easy to update single bulbs. You don't have to pump out all the data to get every bulb to light, but they're really slow. The protocol's quite slow, so it takes a long, you've got to wait, I think it's 10 microseconds for each bit of data to go across the wire, so it's quite slow when you're updating a lot of bulbs.
What's the bit?
It's
I heard around
4 bits on each colour, I think it is. Plus, it's actually got a cool feature. It's got brightness, so you can actually also control the brightness separately from the colour, and that kind of makes it nice. But the bulbs themselves are spectacular. They're nice and big, and they look brilliant. A little bit better than these ones here, which look, they're colourful and everything else, but the visual impact of them is just not there. But they're also not cheap either. So based on that, I started to build lights based on these things. Right, this is an Arduino. It's an Arduino Mega. I'll pass it around if you like. It's not there. This thing's slightly less powerful than an Apple IIe. Okay, so it's got 8K of RAM, which is not a hell of a lot when you're trying to track multiple bulbs. And it's got, that one there's got 256 kilobytes of flash RAM, so you can store your program and everything in there, but your actual working storage is really, really small. This is the smaller version of it. This one's got 2K of RAM. You can't do much at all with one of these. You've really got to work hard. So I'll set one around as well. The beauty of the Arduino though is it's open source, which means there's lots and lots of manufacturers of them, and they manufacture them dirt cheap. The Arduino Mega is about $15 US when you order it from China. So they're pretty cheap, right? You can go through a few of them and it's no problem. Not only that, they come with a lot of expansion boards, and I'll talk through a little bit of that. So this is going to be a bit all over the place because I want to show you a few things. How many people really do electronics, or we just plug and play and use the software? Is there any? A few? A couple? All right, so I'm going to cover a few concepts today. Look, if you've all heard it before or you're bored or whatever, I'll sit down. But otherwise, look, I'll just ramble on and use my hour and a bit or whatever it is that I've got. So why do I build my own controllers? It's significantly cheaper, and it does cost a lot of money if you're buying all the stuff off the shelf. And if you're willing to take the effort to build your own and follow instructions, it can be a lot cheaper. The parts are quite small. It's much more technically interesting. I love knowing exactly how to pump the data out across those bulbs and make it work. And when I show you some of the software and how it all hangs together, you know, I can program it on my PC, simulate it on the PC, know exactly what it's going to look like before I upload it to the microcontrollers and we run the lights. So that's a lot of fun. So you really do get to understand exactly what's going on these things. But why not? For a lot of people, you spend a lot of time focusing on the technology, which means if you're into the visual design stuff, etc., which I'm not real good at, that's why the wife's here. It does take a lot of time away from that. The matrix, which I've got over there, I spent almost 3 months building that and getting it right and getting all the software to work. It'll be close to 10,000 lines of C code that sits behind the scenes and drives it all. So there's a lot of work that goes in behind it. It's definitely definitely less integrated. So you know with the Light Show Pros and everything, you can do the whole property and you can control it all, etc. These things tend to be more standalone. You can integrate them, right? So there's a guy in the States that copies my designs and builds them, and somewhere in Ohio somewhere. And he wanted them to have multiple features, but he wanted them to be synchronized, so they all happened at the same time. So yeah, we added a little bit of code and a couple of wires, and we did manage to synchronize a couple of controllers together, but it's definitely a lot more fiddly. If you're really looking for that whole of house effect, etc., you're much better off going with DMX control system. Definitely more technically fiddly. The patterns can be fiddly to create. I've gone to a lot of trouble to try and make the pattern stuff a little bit easier, and I'll show you some of how I've done that. Definitely broader technical skills required. There is a bit of electronics in it. The electronics is not enormously advanced because it's digital. It's mostly plug and play. It's just 5 volts and connecting the right wire to the right place. There is lots of coding in it, but to be honest, the guys that copy my stuff and rebuild it, they're just copying my code. They don't actually have to write any C code. You don't have to do anything fancy like that. You do need to compile it and load it up onto your Arduino, but that's pretty straightforward to do. And writing the light patterns, I've created a very simple way to do that, so they can actually design the light patterns without ever writing any actual code. There are limits.
Match is gone. Flashing away, yep.
Yeah. It didn't last very long. I can speak up. So my matrix, so I've got an Arduino over there running about a 50 by 19 matrix, about 950 volts. That really is getting pretty severe. I've actually had to create a way to add extra memory in order to manage that, because there is just not enough memory to hold the details of every bulb in that 8K of memory at any one point in time. So I have to shuffle it backwards and forwards from external memory. If I really tried, I could probably push it to about 3 times that size. And at that point in time, I'd probably be beyond it, and I'd have to add another controller and synchronise the two. Once again, not impossible to do, but harder. The other challenge with it is refresh rates. When I say that the WS2811 protocol is really challenging, it is. The routines which actually pump the data out to the lights has to be written in assembly language, because it's the only way to get it fast enough and accurate enough to happen. So it really is pushing the limits of a little microcontroller like this. That being said, there are other microcontrollers on the market, and once again, you pay a little bit more money, you get a different microcontroller, and some of those are a lot more powerful. And these things keep getting cheaper all the time. So lots of reasons not to do it, but at the same time, cost is a big one. There's obviously not a lot of difference. You still have to buy the same bulbs, you still have to do all the same wiring, you still have to package it all up, power it, etc. That's all the same. But the difference is in the software. There's no software cost. You don't have to pay a penny for Light Show Pro or whatever. There's the controllers themselves, like I say, are dirt cheap. And even the most advanced controller and my Matrix controller is getting out there. It's about $20 in parts on top of the microcontroller. So there's not much to them. They're pretty simple. So the Arduino, why? Like I say, it's low cost, and it's low cost because it is open source, right? So if you hop out to Arduino.cc, I think it is, it's got some funny address. It's very well documented. Unlike something like, I don't know if you guys ever heard of the Raspberry Pi. Yeah? So this is basically this is a mini computer, right? You can plug it into a screen, you plug a mouse and a keyboard in, and you can run Linux on it and use it. Problem with something like this is it's not very deterministic in terms of timing, because it runs Linux. Linux every now and then decides it wants to do its own thing, and your program doesn't run at full speed because it's been interrupted. I did try to run the color effects lights off one of these, and every 30th bulb would look wrong because the operating system had gotten in the way and slowed it down, and the lights didn't go right. So I don't use these at the moment. You can in theory program at the metal on them and get it to work, but it's a lot harder. So that deterministic performance is really important with these things. Extending it, the $15 to the Ethernet shield, that actually gets you 2 of them, I think it is, from China, so they're pretty cheap. I'll pass a few other things around here. So you can plug in or attach a little SD card reader. My Matrix uses one of these. I plug an SD card in it, I load a folder up full of images, and it will go through and display the images like it's a movie. These here come as a pair. These are little RF. These little RF boards, so you can plug these into a couple of them and they'll talk to each other with the right code. There's about $3 for the pair. You need 2 pairs if you want to have them talk backwards and forwards, so it's one way. So if you just want to control a bunch of devices, you can use those. What else? We've got the memory chip down here. These I got out of Thailand, a little 64 kilobyte memory chip, which once again you wire into it, and that's how I managed to get past my 8K limit by shuffling data backwards and forwards. So lots of stuff like that. So this is how it works. This is my Arduino Mega. This is how my Matrix works, right? Except that some of these things aren't there. So first of all, need a power supply. The Arduino runs at 5 volts, so I don't need the power converter. I've got another controller up there that I use to run some dumb RGB lights on a tree. And because they're just dumb lights, you have to turn them on or off. They run at 12 volts, and so I just use relays. So you get something like this, which is a 8-way relay control board to switch it on and off. And because there's no, the speed's not really a factor, dumb relays can do that quite effectively. But in this case, I don't need it. The power converters, I don't know if you guys use these, but once again, you pick them up in batches of 10 from China. This one here will do very low current, but if you just need 5 volts out from a 12 volt supply, you can pick these up. Once again, they're $2 or $3 out of China, and I use that to run the Arduino in one of my control boards because I run the lights at 12 volts and I didn't want to run a second power supply, so you can do that. This one here, and once again, I'll pass it around. This one here is a little bigger, and it's a little bigger because you can draw a bit more current out of it, but basically same thing applies. It will convert 12 volts to 5 volts or any other voltage in between. So we need a power supply. Obviously we power the bulbs and we power the Arduino. You can, in some circumstances, need to isolate them. So for instance, if you're running your Arduino at 5 volts and your bulbs are running at 12 volts, you can't just connect them straight up. You need to put something in the middle to convert the voltage. We can talk a little bit more about that later. So I use, like I said, for my trees, I use relays to do that. You can also use hex buffers to do it electronically. So if I was trying to drive WS2811 12 volt strings, right, I'd have to use a hex buffer. So they're just microchips which do the isolation of the voltage. So it allows you to control it with 5 volts but switch 12. Okay, and they're nice and fast, so they can still handle the protocol. And here, for instance, I've got the SD card on my Matrix, and I've also got external SRAM as well plugged into the side. Okay, so this one's a little bit more complex. So there's 2 pieces of this. At the top is what I do when I'm developing my patterns, and down the bottom is what I do when I deploy them. So at the end of the day, I've got a piece of software. Let's start down here and then we'll come back up to the top. So here's my Arduino. Down here, there's an IDE that you download from the Arduino site, which is used to compile your code and load it up via a USB cable onto your Arduino. In order to do that, you need some code. All right, and the code doesn't change. When I change my patterns, it's all stock standard. Right, but there is a header file that I generate, and I'll talk about how I do that in a second. And this contains all of my lights instructions, okay? And when you compile the program, the header file gets pulled in, gets uploaded, and once it's loaded onto the Arduino, it's done. You just turn the power on and the thing will work, okay? Generating the header file is obviously something that gets done up on the PC, and the way I do that is I've created a very simple language for programming my lights and for describing which bulb I want on, or I can actually even draw things like draw lines or draw circles or draw boxes on my display, or display a bitmap or play an animation of bitmaps out of a folder and that sort of stuff. So a very simple language which does that. It goes into a very simple compiler that basically turns that into a bunch of integers, and those integers get loaded up into this header file which can be compiled down here, but it also puts them into a data file, and that data file can be read by exactly the same software that I'm compiling down here, and it displays it on a simulator which runs on the PC. Okay, so you don't have to have the hardware set up working in order to do the development. Okay, not only that, the simulator conveniently writes to a log file, because sometimes when it's not working the way you expect it to, you really want to see what's going on, and the log file lets me do that. So I'm going to show it to you in a minute running. Now I've kind of cheated here. Normally all the parameters actually appear on separate lines because it made it easier to write the compiler. But this is a pattern from my matrix. It's very simple. First of all, I have to tell it how big my matrix is, because it'll run on a matrix of pretty much any size. So if someone else was building it and they had a matrix of slightly different size, obviously you want that to work. The cycle interval is the number of milliseconds that it's going to sleep, or microseconds it's going to sleep between each cycle. So everything's a cycle, and all the instructions within a cycle are executed until it hits something like a do nothing command, which actually forces everything to update. It has some very simple variable capabilities. So here I'm setting a variable called x to a value of 0, and then I'm going to start a loop. I'm going to go in, and here I'm telling it to do something. I'm going to fade a bulb. In this case, I'm going to fade all the bulbs in a line over 20 cycles from one colour to another. Right? I adjust the variable. In this case, I'm adding 1 to it. I force it to update, and I loop back around and the last lot. So what this is going to do is actually take my matrix, and it's going to fade the bulbs progressively down, so it does look like the colours rolling down the matrix. Okay, kind of hard to imagine when you're sort of looking at this, but it's a different way of programming. You can write some pretty advanced patterns this way, and every now and then you can't, and then I get in and I add another instruction which will do something like this. This gives you an idea of the sorts of things that it can do. Most of these commands work on one, or in some cases more than one bulb. Things like adjusting the brightness, so it allows you to progressively fade or brighten a bulb. Setting a fade colour allows you to specify a range of bulbs and fade them between one colour and another over a range. Like I say, you can do things like you can copy bulbs, so you can set up a pattern and copy it elsewhere on the matrix. You can replace a colour, so you can go out and say, find every bulb that's that colour and change it to a different colour. Drawing lines and drawing circles. Drawing lines is particularly useful when you're trying to do some patterns. Bitlit is just display a bitmap, so you create a bitmap, you store it on the SD card, and you just tell it to display. What else have we got here? These ones here are multi-cycle commands, so these are things that you load in and they execute over multiple iterations. So things like rotating bulbs around, so it rotates the bulbs around the matrix, or shifting them, just moving them along, replacing them with a solid colour at the beginning. And things like animate, which allows you to take a folder and display all the bitmaps in that folder one at a time over a series of cycles. Anything else I really want to go there? You can do things like conditionally execute an instruction, so you can actually end up writing some quite complex patterns. So let's run it. Oh.
Rather than getting up.
Yep. It's raining the other night, so I'm hoping it will. Okay. So here's a pattern. You can actually write subroutines. So this one here's the master routine. I'm setting up my matrix, which happens to be 50 wide and 19 deep.
I'm going to wait 50 microseconds between each cycle. The do nothing here is only to make sure that this instruction executes, because the instruction doesn't actually execute until you reach a do nothing point. That forces it to happen. And then this is going to call a subroutine, which happens to be in this folder here. So here's the actual program. This one here, screen's wider than that. Okay, so here we're basically going to blank the matrix out. So we're going to set the matrix all to black with that instruction there. This one here's going to draw some text. Right, so, and the text it's going to draw are these three pieces of text here in three separate instructions. And the reason I've broken it up this way is because each one draws in a slightly different colour. This one here is drawing in red, green and white. So we're going to get an interesting mix of colours. And then we're also going to animate a folder. So folder 5 here is actually the folder that contains all the bitmaps that we're going to animate. And then at the end, we're going to fade it to black. So a very simple thing. So let's have a look quickly at our folder. So here's our folder of bitmaps. Okay, so as you can see, it kind of looks like it's snowing. Not only that, as we go down through the bitmaps, we progressively get to the end, and the snow's all built up, sitting at the bottom. Okay, how do I do that? Well, once again, I wrote a program which generates snow, and it'll generate 200 bitmaps containing snow, and you can decide whether the snow built up at the bottom or not. You can decide how big your matrix is. So if you need 200 bitmaps of snow, it saves you doing it manually. Okay, so let's run it. So a couple of things just happened here. It's going through its test pattern, and there it is. Right, the snow's falling down. Merry Christmas scrolls across. That's just now about 200 cycles. It'll stop, it'll fade to black, and in this case it'll loop back around and start again. Okay? So what happened then was we ran a compiler. The compiler compiled it and created two files. So let's just do it in Notepad. And what it did was it generated a header file. And a header file is exactly those instructions that we just saw in the text file, but in this case what it does is it converts it into a string of integers here, which my program eventually processes. So rather than having to write this, which is quite complex, you just write those simple text files in the file. Okay? It also generated this data file, which I would show you, but it's just a binary file which contains exactly the same content as the header file and enables us to run it on the PC here. Okay? And what you can do then is you can start to merge these together. So I write each pattern and then I write an overarching program that just sucks them all in, displays my whole display, and I can just get each pattern working at a time and then add them all together at the end and say that's how I want it to work. Questions? All good?
With all your bitmaps,
Yep.
the bitmaps aren't stored on your Arduino. They're
On an SD card.
Oh, they are on the SD
Yeah, I
card.
put them on an SD card. So I literally copy that folder and put it onto the SD card, and the Arduino reads it out of the file system on the SD card.
In real time.
In real time. Yeah. Well, it's pretty easy because it doesn't actually have to load the whole bitmap into memory.
Yeah.
Right? It just opens the file up and reads what it needs when it needs it.
I think everyone's going to set up the front.
Right? And that's pretty quick. Right? There's one other mode which I haven't shown here. On the matrix with 950 volts, to be honest, I was struggling to get the frame rate up. So a pattern like this would probably only update 3 times a second, which is not really as fast as I would like. So there is another instruction that I can add here, and what it will actually do is when you run it on the PC, it actually, because it's actually running the pattern exactly like it would do on the Arduino, and what it will do is it will capture all of that data that it was going to send to the bulbs, and it'll actually write that into a file. And then when you run it on the Arduino, it will just read that file. It won't interpret any of these instructions. It will just pump the data out to the bulbs. And when I do that, I can get 8 to 10 frames a second, which is more than fast enough for most patterns. All right? In fact, it all looks a little bit silly at that speed. It's just so fast. The disadvantage of it is some of the things like random colours, which you would normally like to have things randomly chosen. If you do it that way, it's all fixed when it's recorded, so you don't get to see it. Okay? All right. So, I wanted to, do you want to see me deploy it onto an Arduino and see what that looks like? Anyone interested? Yes? All right. USB cable. USB cable. Does someone have that Arduino that was floating around? This one. That one, that's it. All right. So really not hard. It's just a USB. You stick it in. Stick it in. The Arduino starts to run. So this is the Arduino software that you just download. It's pretty primitive. One of the reasons why I actually write my code to run on the PC, and the code inside, it's got all these pieces of code which are very specific to the platform, and you sort of just say, well, when you get to this instruction, don't do this, this won't work on the Arduino, do this because we're running on the PC, and when we're running on the Arduino it switches over. So let's get my tree code. Okay, so here's the tree code. As I said, it's all C++. Right, this here happens to be, so this here happens to be PC code, hence the hash defined is it a PC versus the code further down, which works on the Arduino. So to deploy it, it really is as simple as clicking on the arrow. Right. And if you're reusing the software, once you've replaced the contents of the program.h header file with whatever header file you generated using the simulator, this is all you have to do. Compile and deploy. Takes a little bit of time, so it's currently still running whatever program was on it before. It compiles. Oh, didn't like that.
Wrong combo.
Was it? Yeah, so it was stuck on 6 on the last board. That is annoying. Every time you plug a new machine in, it allocates a new COM port, and I got more of these so you can poke a stick at. And this is the other annoying thing. You compile it, and it's got to recompile it all again, even though...
That's when you have different processes too on different boards.
Yeah. Oh, still didn't like that either. Oh, I know why. Sorry. I do have to tell it what sort of board. The Arduino Uno is quite small.
It's a different processor too.
Yeah, it's an older processor, smaller. Where's the Mega? There it is. It's going to go nuts in a minute when the serial kicks in and it starts to send the data over. Alright, so now it's uploading, so the lights are going nuts. One of the other cool things you can do is you can actually have the Arduino send strings back to the PC telling you what's going on. So it's done uploading, so you can display this board here. Ooh. Board rate's wrong. There we go. You can see this one here happens to be dumping out how much free memory the Arduino has at any one point in time. So I can tell when I'm running close to running out of memory, etc. There's actually, in my code, I have a pattern where I use, let me show this to you. So this header file here, global. So this here lets you control exactly what happens, and one of the things I can do is control how much messaging is actually dumped out by the thing. So that allows me to compress the program down when I'm using it in real time, but when I'm doing development I can turn on extra features and the like. So that's happily running along. Alright, I then wanted to go on. Alright, so talk about one of these. This here is a logic analyzer. Okay, when you're doing actual on hardware development, etc., sometimes you really need to know what's actually going on the wire. Even when you're running other things, sometimes it can be really useful to see what does this signal actually look like. Is it really coming out the way I expect it to? And this little logic analyzer here is pretty cool. There's no plugins in. This Arduino here is running exactly the same program. Okay. Power the Arduino up. All right. So what we've got here is we've got an Arduino running quite happily. You can see that it's running my tree pattern, so it's displaying various lights. And we're going to run this program here. We're going to click start. And what it's done is it's actually captured the data that the Arduino is sending to the lights. Now you can do this on anything that's sending 5-volt signals. If you're running 12 volts, it's not going to work. You'll fry the digital logic analyzer. And then you can actually zoom in on these signals and see what's going on. So here we have a bunch of data being sent on channel 2 here. This is actually sending a 0, and you can tell that because this is 1.25 microseconds long, followed by 1 microsecond low, and that tells me it's a 0, etc. So these are really powerful when you get into trying to debug exactly what's happening on the lights, etc. The downside of it is it's only telling you when it's 0 and 1. So if you really want to, if you're getting power signalling issues where your lights seem to be working sometimes and not quite, you might have a signalling issue. And if you want to debug those sort of things, you really need something like an oscilloscope. And we'll set this up over there on the oscilloscope in a minute. You can see what the signal actually looks like. Slightly different. So that's a logic analyzer. Like I say, they only work on 5-volt signals. They only show high versus low. They don't give you any idea about the quality of signal, so it might be marginal. If you've got long wire runs, etc., you can lose some signal quality. It might round off the signal, or it might spike up and take a while to settle, and that can throw out your device. One of the things I didn't show, it's kind of shown down here, is depending on the protocol, and unfortunately the WS2811 protocol is not one of them, it can actually interpret the protocol for you and actually show you what it looks like in hexadecimal or something like that. This one here is from a company called Soleil. There are cheaper versions available. Once again, you can pick them up on AliExpress. The cheapest ones are about $15. I probably wouldn't go in for that price point. Some of them don't come with packaging, so they're just a bare board. I probably wouldn't go for that either. But you can pay anything, like I say, from $15 up to about $150 for a logic analyzer. The oscilloscope's a lot more expensive. Even the cheapest ones on AliExpress are about $250 a pop for a digital oscilloscope, so it's not a cheap piece of kit. JCar, you can pick up one at around $500, so even more expensive. But you do get what you pay for with oscilloscopes, right? You pay a cheap price, you tend to get a fairly cheaply made device that's pretty slow and not great. The digital ones, to be honest, can do the logic analyzer thing as well if you set it up properly and take all the time, but it's a bit like overkill, particularly at that price. But the beauty of it is it does show the signal, and we'll take this back there and I'll actually show you what those ones and zeros really look like, and they're not as clean as the digital analyzer would suggest it is. Okay, you see this? You can. This is a circuit to get to know and love. A very simple circuit, a resistor and a transistor, but if you ever find yourself in a situation where you need to do level changes, this is all you need. So if you've got a 5-volt signal and you need to switch 12 volts, this will do it. Right, you've got a 12-volt signal, you need to switch 5 volts, this will do it. Right, just the appropriate choice. A resistor, typically around the 10K mark, is a pretty good bet. Right, voltage that you want on the output and the voltage you want on the input. And what happens is when this goes high, this switches on. The only thing you might want to do is put a really big resistor across here just to make sure that when it's off, it's clamped to 0. So if you're in a situation where you need to do that, it's a very, very simple circuit. The only thing is, you need to be very careful about how much current you draw. If you're going to draw a lot of current, then you're going to need the right sort of transistor here. But if you're just doing signalling on a WS2811, or if you want to build a very simple circuit to turn off when it gets dark, turn on when it gets dark, etc., you can do that with a circuit like this. You just need to put an LDR, a light-dependent resistor, on the top here, and a big resistor down to the bottom, and it will switch on or off at dark. But like I say, yeah, if you're going to draw a lot of current, if you're going to run the whole string of lights or something off that, you're going to need a decent transistor with high power, because it really heats up, and you're going to have to put a heat sink and whatever else on it. Yeah. The other sort of things is like the SN7407. These are hex buffers that I was talking about. These come in a package like a microchip, and you can actually do this with 6 at once using one of those microchips. Once again, you have to be really careful that you don't draw a lot of current through them, because they will heat up and actually fry themselves pretty easily if you do. So, what else do we have here? A couple other things I just wanted to show you. Breadboard. If you're going to do any electronics development, this stuff's magic stuff, right? It's just a simple board. It's got a stack of holes in it. You can plug transistors, resistors, etc. in, and you can build circuits. They're actually joined together underneath the surface. You can't see it. There's a couple of rails at the top and the bottom which get run horizontally across the board, and then the rest of them run vertically up to the middle. And it lets you put microchips and whatever else in and build your circuits, test that they all work before you try and commit them to a soldering iron. These are magic. Search on the internet for this. Everyone's got an old PC laying around, an old PC power supply laying around. Right, you throw the computer out, these things are often, you know, sitting around. For, I don't know, $15. Couple of connections on here. There's a few changes you need to make inside it. 5 and 12 volt power supply, perfect as a bench power supply. Right, absolutely magic stuff. Beats paying $150 for a bench power supply J-car. Right, $15 is good value in my view. What else do I have? Okay, so we went over this last year, but for the new ones here, this is the board out of a regular flasher. I think this was the Big W light set. You know, it comes in a white box. It's got a little button that you press, and it goes through a bunch of patterns. Well, I don't know about you, but most of the time when I'm using those lights, I either want them all on, I want them all off, and when you turn the power off, they go back to their default pattern, which is annoying. Okay, so if you want, you can actually change these controllers really easily to make them all on all the time. It's just a matter of shorting out these transistors at the bottom here. Right, and if you look carefully on this, when I pass it around, you'll see soldered onto the back here is a little bit of wire. So just above the 2 wires that are joined on here, I put a little bridge across a bunch of these. So this is a 2-channel one. It controls 2 sets of lights. And what I've done is I've actually shorted out 1 channel. So one of the channels is going to be on all the time, every time I turn this on. Okay? Another useful thing to do if you want to do that. All right. I think that was all I had. Other than if we want to go back, I'll plug it into the oscilloscope and you can see the signal on the oscilloscope. I don't know how you want to do that.
Do that later.
Do that later?
Do that later, yeah. We'll break the morning tea, yeah.